This is our second lecture on Feynman lecture, volume 3, chapter 2, the relation of wave and particle wave point. In this video, we will cover all these topics. So first of all, probability wave function. Let's say we have amplitude in this form, exponential iota omega t minus k vector dot r vector, where omega is particular frequency, k vector is a wave number. So classical limiting situations, let's say energy is equals to h cross omega and p momentum is given by h cross into k vector of a particle. Now here we have no knowledge of position of particle. Okay, now if we square it, we get this equals to 1. Now, which is a constant, which means finding of particle is same at all points. Okay, so if position is known, now we are considering that if position is known, then probability of finding it in different places must be confined to a certain region. Let's say that is delta x. Okay, if we know the position, that must be confined to a little space, that is, let's say that is delta x. Now, what we see here, we see these curves, high curves, low curves, greater peaks. Then as we moving away from it, it becomes a straight line. So on edges, this probability of finding the particle becomes 0, which means this A becomes 0 and ultimately this momentum becomes 0. So there is no unique wavelength, as you can see, which means we have poor knowledge of this momentum. Uh, okay. So what can we conclude? That perfect knowledge of energy or momentum is equals to complete ignorance of position. And if we have the knowledge of position, we have a poor knowledge of momentum. Now, measurement of position and wavelength, we have a slit and part, let's say there is a light source and light is coming in this way, and here is a slit of size B, and there is a screen. Okay, so let's say we have a slit and particle are coming from far away with certain energy. We are going to concentrate on vertical component of momentum. So in classical sense, let all particles have certain horizontal momentum, let's say that is P naught, and therefore vertical momentum Py equals to 0. Okay. Now particle neither moving up or down because it came from a source that is far away. So these are our consideration, and all these things are definitely known before light passed through the slit. Now we are focusing on the situation when light passes through this slit. We know the position vertically now with considerably accuracy of plus minus delta B, because we know the size of this hole or slit. That is, uncertainty in position delta Y is of order of B. Now, there might be a wrong perception, that is like once we know the horizontal and vertical momentum, so we can say delta Py is 0. But that is wrong. We once knew about this momentum that is just horizontal, and we know that the Py was 0, but we don't know it about anymore. So here I make a little table of it so that we can understand it better. So in before, momentum is known, but no knowledge of position. But after, we have poor knowledge of momentum, but uh, uh, position is known. So why vertical momentum is not 0? That can be answered in this way, that according to wave theory, there is spreading out or diffraction of waves after they go through the slit, just as for light. There is certain probability that particle coming out of slit are not coming exactly straight. So we have rough idea of spread, like vertical spread. Let's say Py equals to P naught delta theta. Now this delta theta can be given by this lambda by B, where lambda is wavelength and B is like size of our slit. So narrower we make slit, wider the pattern gets, and more is likelihood that we would find that particle has sidewise momentum. Thus, uncertainty in vertical momentum is inversely proportional to the uncertainty of this y. So we have this delta y or delta py which is greater than h cross upon 2. Now, above equation refer to predictability of a situation, not remarks about past. It would not be good to say, I know what the momentum was before it went through the slit, and now I know the position. So it is like I know this is going to happen. Like you understand? Uh, at the moment we are making the judgments, system may have changed to some other uh, state. So other way to measure of this momentum. So if you don't know that a resolving power of gradient can be given by this delta lambda by lambda equals to 1 upon nm, whereas n is the number of lines and m is order of diffraction. Now we can divide by lambda on both sides. We get this situation, this equation over here. Now further, if we modify this equation, we get this delta k by 2m, which is equals to 1 by L. Now this L equals to nm lambda. This what we get. Now important point is that the finite train can't count the waves in it precisely. We have tried to emphasize that these are property of wave alone, but in quantum mechanics, we interpret the wave number being a measure of momentum, which is p equals to h cross k. Now this delta p equals to h cross delta k, and delta p is approximately equals to h upon delta x. So limitation of the classical idea of momentum, which can be. So quantum idea of momentum, the particle is not a point, it is described by wave packet. Localized particle is wave packet, which is superposition of many different momentum waves. A short wave packet has large spread of momenta. Now, crystal diffraction, in order to obtain a strong reflection, the scattering from all the atom must be in phase. So there can't be equal number of phase in and out, or wave will cancel out otherwise. The wave to arrange things to find constant phase, planes make equal angles with initial and final direction. So this you all know that 2d sine theta equals to 1 lambda, where d is spacing between two adjacent planes. If spacing of nearest planes are less than half of wavelength, in that case we have no solution for above equation for n. If wavelength is bigger than twice the distance between adjacent planes, then there is no side diffraction pattern and the light or whatever it is will go right through the material without bouncing off or getting lost. So neutron short wavelength means they are interacted with this graphite. Now this let's say this is here the input wavelengths. Here is graphite. Now, what happened that the long wavelength means they didn't interact with the graphite. Whatever is coming out, that didn't interacted with this graphite. Now, and short neutron, lambda neutron or short wavelength, they interacted with this graphite and just split it otherwise. So this explains the wave particle duality of matter. If one plot we can see here a plot. If one plots the intensity as a function of wavelength, we get nothing except for wavelength longer than a certain minimum. So if we keep going right through like light through glass and are not scattered out the slides. So this is the lambda minimum, and as wavelength increasing, this is our result. Now, the size of an atom, suppose we have hydrogen atom, there is a spread in position of order A, so spread of momentum is roughly h cross upon A. So momentum must be order of h cross by A. The kinetic energy must be h square upon 2m A square. So uh, uh, we can have this like total energy in this form. After that, when we differentiate it with respect to this A, we get uh, this kind of solution over here. Now, uh, what we can do, we can calculate it, and we found it 0.58 angstrom. Just for dimensional analysis, we avoid the constants such as pi and 2, etc. So this total energy becomes me raised to power 4 upon 2 h cut square, which is equals to minus 13.6 electron volt. So important points to be noticed that the negative sign means that the electron has less energy when it is in the atom than when it is free. It means it is bound. If electron is squeezed on the top of nucleus, we would know its position very precisely. This means its momentum and kinetic energy have to be large according to uncertainty principle. So this uh, this compromise made by electron and nucleus. Now this uncertainty principle can also explain why matter is solid. Uh, is it classical or quantum effect? That we can say, we can understand in later discussion. So if we squash or if we force the wall, then we are trying to confine the electron to a smaller space. Now, confining the electron skyrocket their energy, uncertainty principle. Now, atom will resist this, and this resistance is what we feel as a solidity of matter. So you can see if I'm trying to confine the electron to a smaller space, then energy will boost and uh, 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 we feel this repulsive force, or I say a resistance. So this resistance is felt as a solidity of a matter. The main conclusion is that the solidity of everyday object is a quantum mechanical effect. Now we are going to understand this energy levels. So electron can jingle and wingle in more energetic way. According to quantum mechanics, in stationary conditions, there can only be definite energies for an atom. So frequency of light, which is liberated in transition from, let's say, energy E3 to energy E1, can be given by this. We can find the frequency like this. Now, similarly, transition from E3 to E0 can be calculated like this. Now, what if we want this E1 to E0? You can see, firstly, I'm coming from this E3 to E1. Then I'm coming from E1 to this E0. So, firstly, I came to E1, then E0. But what if we want to go directly to E0? So what you will find that this W3O will be equals to sum of these two frequencies. So important points to be noted that when wave is confined to a limited space, it can only vibrate at specific discrete frequencies of normal modes. So applying this to an atom, it is a wave confined by the electrical attraction of the nucleus. Just like sound wave in an organ pipe, the electron probability amplitude wave must fit into confined space of atom in a stable standing wave pattern. Only certain specific wave patterns fit nicely without cancelling themselves out, each of these stable wave pattern corresponding to a definite resonant frequency. Now, in quantum mechanics, the frequency omega of the amplitude wave is directly related to energy E of state y, E equals to h cross omega that we already uh, discussed. Therefore, confined wave means a discrete frequency, means discrete energy. So philosophical implication is that there are three common misunderstandings: the observer effect, that consciousness shapes reality. Second is the role of theory, that science should only use measurable concepts. Indeterminacy and free will, that quantum randomness explains human freedom. Myth 1, the observer creates reality. The myth, just looking at something changes it with our mind. Now, the Feynman says the measurement is a physical disturbance. So, the simple analogy is if we're trying to see a house of cards, uh, your light or touch will knock it over. It's physical bump, not a mental one. So, this is about unavoidable physical interaction, not the power of human consciousness. So, second is science is only about measurement. If you can't measure it, it has no place in science. This is the myth. The Feynman truth says the science needs useful idea to predict outcomes. The simple analogy is a chef uses the idea of flavor. You can't measure it with the ruler, but it's essential for creating good food. So keynote is that the goal is prediction. Concepts like electrons path are useful tools, even if we can't measure them directly. So quantum randomness explains free will. So quantum physics makes everything random and this gives us free will. The Feynman truth says the classical world was already unpredictable. The simple analogy is a game of pool. A tiny immeasurable error in your first shot makes the entire game unpredictable after just a few bounces. This is chaos theory. So you can't use quantum mechanics as a special explanation for free will. The universe was never a perfectly predictable clock. Thank you so much for being with me.